talk kind of has a few different phases. The first third is called breakup. Parts. Information. So start at the beginning. So part of created by the issue. Something that's not really clear about nature. So this is something that I'm really interested in, and especially the experiment. But the strength of is and there are different ways that the problem is actually part of strength. So the reasons lower that that overall weakens the continental sphere that will allow things to break. But no matter how you slice it, right, really the block surface controlled by this here you have two particles, two nodes. I'm particles. In some cases, it's not don't want to just look at suture. So one thing that lots of separate student north body southern body is suboceanic. So you'd be looking at in the mantle sphere. And really interesting here, it implies this is bit. What was really cool is that we could start identifying in new 3D seismic bases. So we're looking at this section. Really in between these two. And see what the high points here. Subcontinental detachments towards the ocean. Yeah, that's interesting.
Okay. We're gonna have to mute that. Okay, how does this sound for everyone online?
You might have to turn up your volume though.
Yeah, I have my volume turned up.
Okay, much better.
Okay, sweet. Okay.
Yeah.
Sorry for that. All right, thank you for bearing with me. All right, anyways, what was I saying? Yeah, so you get these continental detachment faults that dip towards the ocean that start to exhume this subcontinental mantle down here. So you can see where the fault comes through here. And this, so, you know, there's this whole area, there's multiple lines coming across it. And then there's a transition zone where these faults become overprinted by detachment faults with the opposite versions dipping towards the land. And that these detachment faults have this very distinctive sigmoidal, anastomosing structure. And these are happening in the, and these are occurring in the upper mantle. And between these two systems of faults, you are exhuming the lithospheric mantle up to the surface. And as you move across, it's especially visible here, but as you move across, what ends up happening is that SDRs, which start out very thin, get thicker and thicker and thicker and thicker. And then in the footwalls of these high temperature shear zones, you start forming layered oceanic crust just through an increase in intrusion. So it's really interesting because then you finally get to see some of the structures in the mantle that are controlling deformation as you move across the rift to drift transition, as you transition into true oceanic crust. So, so that was what was seen in the Ivory Coast. We also wanted to see what processes control that transition through numerical modeling. Because that gives us a view of the process, not just single snapshots. So crust, lithospheric mantle, asthenosphere. The red is these high temperature detachment faults that occur through damage rheology, dynamic grain recrystallization. The green are the normal, detachment faults that are happening in the crust. This glowing purple to yellow spot, that is where you're going to have magmatism. And that magmatism is eventually going to start underplating as yellow dots here. And the boundary conditions here, we have a constant extension rate that we get to prescribe at the beginning. Eventually you form these, anastomosing detachment structures. You get these domes of mantle. And eventually the model, we turn the model off and it starts to become unrealistic. Because we don't have a lot of volcanism, we're not actually modeling the diking process. So as soon as we start getting these, symmetric, flipping core complex looking stuff that looks a lot like a ultra slow spreading center, like the Southwest Indian Ridge or the Gackle Ridge, we say, okay, cool. This is where oceanic spreading has started. And now we can look at the structures and see how realistic this actually is. Turns out pretty close. That was one of many different models that we ran. But here it is in kind of zoomed in. This is that same line from before. And then here it is matched to the model. And the important thing here are looking for these homologies, these structural and temporal similarities between the two, because process-wise, they're very different. One's the real world, one's a model. So, these structural and temporal and spatial relationships are really important. And what you get are the same oceanward dipping detachment faults through the continent, this doming of the mantle where these two detachment fault systems intersect, and then you have increasing magmatism and a more symmetric high temperature detachment fault system as you move out towards the oceanic crust. So that's really, really exciting. And then when you put this into the greater context of how we think that these systems evolve, you can actually start to identify, so the Ivory Coast profile covers the whole thing, at relatively shallow depths. Stuff like Lonzo, which I talked about earlier, would be a more narrow part, but it's down deep at the very bottom of what you can see in the seismic. And then other places around the world, like Nurali in the Ural Mountains in Russia, and the Aeroplatanops also in the Italian Alps. These would show upsection portions of this framework for magma pool rifting. And that framework begins with this idea of, okay, at first, you have these stresses that are, everything's gravitationally collapsing. You have upwelling as a result that causes decompression melting. That these two systems of faults initially are separate and then couple later on. And then as they couple, they go from asymmetric to symmetric. And as this process moves forward and you start creating oceanic crust, the presence of melt pushing up from below, because it's hot and buoyant and it wants to push up from below, you're going from gravitational collapse more towards, kind of like this dynamic uplift. Which isn't a new idea. Polyakov and Buck came up with this, around the turn of millennium, where the idea of you initially have this top-down, collapse of the rift, and then as you transition into seafloor spreading, it starts to kind of run itself as this decompression melting applies stress from below. And kind of bringing this back all the way to the, to the question at the beginning of like, how does this process happen? If you look at the forces, right, because we have a prescribed extension rate, we're not applying a stress, we're applying a velocity. So the force required to maintain that velocity and actually break apart the lithosphere as a function of time in the model, right? So that's this line. And then compare that to what you would get from just like, like classical ridge push. And what you get is that during the early stages, you need some extra force in order to actually break apart and start that continental rifting process. But once it gets going, it can propagate itself. And that means that it could propagate along, if you already have a rifted area, it could propagate along the rift tip to adjacent areas. What that means is that, okay, so for supercontinental propagation, you need an initial push. And if you look at the order of events for like the breakup of Gondwana land, for instance, they don't start at the middle, they start at the edges with trench rollback. And then that, back arc extension actually propagates upwards and into other oceans. So this is kind of the direction that this research was pointing. That you could actually, it's, not far field stresses affecting the interior of the continent, but you break the continent at the end and then you propagate inwards, maybe following weak zones like origins or mantle plumes, which is in line with a lot of these ideas from like Cortelot in the 90s about, rifts propagating towards plumes instead of starting at plumes and propagating away. So that's what we were at here. And then Getting into the second part, explaining the sudden shift into taking these same models and the same idea of thinking and applying them to a completely different planet. Well, that started because one day Luke walks into my office, throws this paper down on my desk and goes, hey, look at this. You know, you have these sigmoidal blocks and these really complicated, fault structures. It looks a lot like, this high temperature detachment, faulting that we've been talking about, for the mantle. But here it's happening on the surface of Venus, which makes sense. The surface of Venus is 470 degrees Celsius. So your brittle ductile transition is going to be pretty dang shallow, and you're going to have low-grade metamorphism up near the surface. I was like, oh, this is really interesting. Maybe we should start playing around with these models because it looks a lot like what we see at like Lonzo and in the Ivorian margin. And I didn't realize the rabbit hole that would send me down. It completely changed the direction of what my PhD project ended up being and kind of changed the whole course of my career. Because before I was thinking, oh, I'm going to do supercontinent breakup and like a rift in margins and the history of plate tectonics on Earth. And now I'm applying to places to, kind of pursue work and like, okay, what are Venusian geodynamics like? Where did Earth and Venus diverge and all these other things? So I'm going to back up a little bit and talk about kind of like setting up the problem of why these two things are related and why I think this is really interesting. Turns out Earth and Venus are perfect points of comparison with each other. They are a very similar size. I think Venus is 93% of Earth's mass. So they're very similar surface gravity, very similar bulk composition. There have been in situ measurements through X-ray spectrometry of the surface, and they come back looking exactly like more basalts, at least at the 4 places where we have data points from. So they look a lot like Morbs, and they're also formed in similar parts of the solar system. There's a great thought experiment where, like, if you were an alien on the Alpha Centauri solar system, and you had this brand new telescope, the Wayne's Jet Space Telescope, and you pointed it at Earth, and you started looking at the mass, the composition of the atmosphere, and you started looking at the solar constant, Earth and Venus would look pretty similar to each other. They both count as far as like planetary astronomers are as being Earth-like and potentially habitable. They're obviously not, though. Venus has no oceans. It's got this runaway greenhouse effect. It's got this enormous atmosphere where it's like something like 92 atmospheres at the surface. It's got no plate tectonics. It's got no internal magnetic field, and it's got no signs of life as far as anyone can tell. Earth is the opposite in basically every single respect. And that is really interesting because why did they diverge? When did they diverge? And what kind of activity does Venus have? And what does that tell us about, like, theoretical frameworks for just how do planets evolve? So here's topography and bathymetry for Earth. Here's the topography for Venus. They are very, very, very different, but Venus also doesn't necessarily look like Mars or the moon covered in craters. It's fairly well complicated, and it's kind of an open question about what is going on there. You look at the hypsometry, right? You get the classical bimodal distribution on Earth that represents the continental and oceanic compositions. That doesn't exist on Venus. So as in bulk, Venus seems to have a uniformly basalt composition. Maybe there's some regional variation, but we honestly don't really know. But it's clearly not plate tectonics. You look at the cratering record as like a proxy for the age of the surface. The more craters that you have, the older the surface should be. Kind of vastly oversimplifying it, but because the size of the crater matters as well. Here, one of these 6 panels is actually Venus. The other 5 panels is a random distribution of dots. The surface of Venus is pretty indistinguishable from a random distribution. Here it is for it's this one, by the way. This is the actual distribution. This means that and because there's only 900 craters on the surface, there's only a couple options. Maybe the whole surface is a uniform age. Maybe it's being resurfaced randomly, or maybe it just represents an average age of the surface. And there are some regions that are younger, but they're pretty small and localized. There's a lot of room for interpretation about what kind of activity and how old the surface of Venus really is. Also, we know also the rheology of that, lithosphere that is also important for determining how tectonics manifests is also, not very well quantified. Here's an example of like a pyrolite, and water composition, or sorry, temperature geotherm for the Earth, for the continents, and for the oceans. And then here's 3 different options for Venus. And depending on the heat flow you pick, and also this depends on like how much CO2 there is, how thick the crust is, and also, how dehydrated the crust and mantle are. You can produce wildly different tectonics on Venus. And so this is the rabbit hole that I fell down, was like, okay, so what is the tectonic style? Like, is this stagnant lid? Is it this episodic that switches between being completely stagnant to suddenly all subducting in only a few million years, and then, the whole cycle starts over again? Or is it some completely different concept? Like people have proposed ideas like plutonic squishy lid, deformable lid, globally fragmented, flake tectonics, plateless tectonics. There's a whole family kind of exotic geodynamic regimes that people have proposed to explain, Venus's geology and geophysics. And this is an area of active research. So kind of bringing this back to Earth a little bit. One of the key features of plate tectonics on Earth is the mid-ocean ridge. Outlined in red here, it's this globe-girdling, single extensional environment that is more or less continuous. It's the youngest feature on Earth. It forms in basalt crust, and it's where you're generating new material. That's what's dominating the resurfacing on Venus. And then all this stuff gets transported laterally until it is subducted away into the mantle thousands of kilometers away. Venus has something similar, yet very different. It has this global rift network that is also globe-girdling. It's also an extensional environment. It is also the youngest feature on Venus, with a really important asterisk, and I'll get to that. It also forms in entirely basalt crust. However, just by looking at this, you could tell it is not continuous. It's a bunch of subparallel sinuous segments that are all more or less linked to each other. And also they seem to link these topographic highs and these other larger features. So like the driving force seems to be a bit different. And also there's no obvious place where this could be subducting. So if you are generating new crust here, then it's got to be balanced out somewhere, but we don't know where, and we don't know how, if this is where new crust is being generated. So that was the question that I really wanted to answer, was like, okay, if you tried to do a mid-ocean ridge on Venus, would it end up just looking like, this global rift network, or is that not a good analogy at all? And so that also brings to the question of like, where is new crust being generated? And also really importantly, if it is being generated there, where is it being recycled to? So kind of zoom in a little bit on one of these rift segments, or some of these rift segments. There's 2 features that I really want to bring up. Rifts on Venus are often called chasmata. Planetary science has its own nomenclature for naming features. But chasmata, for our intents and purposes, are basically just rifts. They are pretty complicated, but they more or less, they don't really look like mid-ocean ridges. They look a lot more like continental rifts on Earth. And they also seem to link these large volcanic regions, such as, like, they call it the BAT region for Beta Atla Thamus. But that's that big triangle region on the previous page. Also these areas such as Aphrodite Terra, and these absolutely massive circular features that are Artemis and Quetzalcoatl Coronae. And speaking of the Coronae are these morphological features on Venus that are very poorly defined. I think the official definition is any tectonomagmatic structure that is circular that isn't a crater. I think is the more or less what the working definition ends up being. But they can be very small, they could be medium, they could be absolutely massive. Like this one is Atahensik. That's a good 1,000 kilometers across. The Artemis and Quetzalcoatl can get up to 2,500 across their widest point. So there's a huge variation in size. There's a lot of variation in morphology as well. We also know that at these chasmata, in that these coronae are often associated with or even embedded within, that the heat flow estimates are consistent with modern day activity. Now, the error bars in this are huge because they're derived from models of the elastic thickness, but they're about like 110 milliwatts per meter squared plus or minus 80. So there's a lot of room, but it is consistent with the CDA. Like there's some level of activity that could be happening at these features. They're also the youngest features on the surface in the sense that the error bars on their age is larger than the estimated absolute age. So again, like there's a lot of uncertainty, but they seem to be younger than most of what's on the surface of Venus. They also, similar to continental rifts, have pretty low degrees of extension. They're not like mid-ocean ridges where you have, thousands of kilometers or miles of extension, as you open up this ocean basin. They seem to be pretty limited to, less than 70 kilometers of overall extension at most. So once again, we use GeoFlack to set up a whole other set of models. This is a pretty different model from the one I was showing before earlier. For instance, we aren't modeling magnetism. What we're really interested in is what does spreading look like on Venus. So we've prescribed a crustal, formation rate. So we're adding new columns at a prescribed rate at the beginning. And that rate is independent from an extension rate, which we can also prescribe. It's similar to what we had before. We can also vary the heat flux. And we also have these other, phases worked in. So like, this is basalt crust. These are the two different layers of mantle. That yellow is the high temperature shear zones that I was talked about before. But this black, which gets introduced into this black is eclogate phases. On Venus, because of the elevated geotherm, when you have upwelling, you can actually create metamorphism just by moving the temperature or moving into a hot, moving the temperature, which is very different from Earth, because on Earth, when we think about eclogite, we think about it in terms of subduction. But because of the higher temperature and lower pressure, it flips on Venus, where you have to start thinking about eclogite, in the context of extension. It gets pretty weird. So this is the model that we have set up. We ran this a bunch of different times, but really what we end up with are these three big overall regimes based on how we're varying the extension rate from 1/10 of a millimeter to a centimeter per year, and then with the addition rate of new crust along the same domain. And then we also just have a binary variation of Earth's heat flow between 50 and 80 milliwatts. So both kind of assume a certain amount of activity. But the key thing here is that what seems to control morphology is the rate of crustal formation, right? Because these, between the yellow, which is this regime here, where you have very low extension, you have high extension, very low rates of addition. So you're bringing a lot of new material up to the surface. You can't accommodate that extension, so it's just this upwelling of the asthenosphere. That's in yellow. These steady state, where you're actually able to replace the new material that is you're able to fill in that accommodation space with new material. That's in the middle here. These are these two different shades of blue. And then there's this over-thickening case where you cannot accommodate the new material. For whatever reason, you're over-thickening the crust. And that creates this very distinct morphology, and that's in red. I'm going to get into this in more detail in later slides, but the key point here is that, there's these diagonal lines that split the two different regimes, the two different heat flows. So it really is a relative rate of crustal formation and extension that controls rift morphology within the model. And it falls down to these three different regimes. So here's the middle regime, the steady state regime, the stuff that's closest to seafloor spreading on Earth. Where what you're doing is you're at the same rate that you're creating new accommodation space, you are adding new material into the middle. And it's a pretty straightforward thing. You do get a little bit of eclogitization that is dropping off and eroding away at the lithosphere, but it's not a whole lot. But what you do get is you do get this new crust that kind of gets wider and wider like seafloor spreading. Wait, that work? Yeah, that worked. That was weird. So, and it kind of comes in two different flavors. There's an asymmetric flavor, which is the one that I show here. And then there's a symmetric flavor, which is here. But just to kind of like get you guys' heads around this fake block diagram, here is the surface's topography. This is the time direction. And then this is the actual like 2D structure of what we're doing. So it's not really a block diagram. It's not showing space, it's showing time. But the idea here is that you initially start with, this, like axial rift, and then that spreads out and splits. And because of this asymmetry, where sometimes, and I think this happens for like stochastic regions, where the most of the extension takes place and where you're adding new material tends to partition. And that's how you get asymmetry. This is kind of similar to what you see at like, the Nazca Ridge or in other mid-ocean ridges on Earth, where you can actually have, at least in the case of Nazca, 90% of the accretion is happening on one side of the mid-ocean ridge and 10% on the other. So you can get a pretty asymmetric setup, and that's kind of similar to what's happening here. But these are the kinds of profiles that you would get out of that kind of thing. For the symmetric version, you kind of get these just like really simple raised flanks. It looks a lot like a classic mid-ocean ridge. These are the two versions. When we start applying this to actual rift systems, though, it's not, to kind of spoil things, it's not a great fit. So here is Hecate Chasma, which is this rift system here. When you look at it, it looks like a fairly typical half graben, which is not something that this spreading idea is able to, really well like match. If you squint, you can maybe convince yourself that, oh, maybe this is a half graben, this gets eroded, but there's no evidence of any kind of like structural, complexity on the interior of this rift. Right, so this is the black line is just the average cross section across that whole entire rift segment. This one right here, and then all the smaller lines are just all of the different lines stacked, end to end. So it's not really a good fit. There's a similar story when you start looking at like the Parga chasmata and Latona chasma, is that there's all this kind of complexity that you'd associate with like continental rifts that doesn't really work with this idea of, oh, well, maybe, spreading just looks different on Venus, where you have this high temperature, high pressure surface. So these diagnostic features of like this, this symmetry or the or that like broad asymmetry is really difficult to match. So it's not very convincing. On the other hand, oh wait, that's supposed to play. On the other hand, right, the hyperextension regime, where you have no new material is being added, you're just pulling on the sides. So you don't have anything to fill that accommodation space. So you just create this, like just this normal looking rift with no new material. That produces profiles that look like this big, broad bowl shape, or, this kind of messier, but overall still like deep, broad feature. That, if you squint, does look like some of the rifts, like Southern Devona chasma, and also Rona chasma, and a few other features. They do tend to fit some of them, at least the symmetric rifts. But that also could just be because, these are full graben features. And when you don't have any new material to add in your rift, if you don't have spreading, you just naturally want to create a full graben in the model. So, it kind of seems to show that the global rift network maybe isn't the best analog to the mid-ocean ridge, kind of confirming through modeling what was suspected just from the surface morphology. So if new crust is being formed here, it's not to the same extent as Earth's mid-ocean ridge, and you definitely don't have the same degree of extension at the Earth's mid-ocean ridge. So it gets a little bit, so it doesn't really work as a model. That being said, there's like some locations where it does sort of work. And by some locations, I mean one specific unique location on the whole planet. This is the famous Artemis Corona. It's something like 2,500 kilometers across, this massive circular feature. It's been identified for fairly obvious reasons as maybe this is where ephemeral subduction, or at least regionalized subduction, is occurring. And this is all rolling back, and maybe this could be a back arc basin of some sort. When you look at this internal structure, so here's that asymmetric spreading case that I was talking about before. It does seem to kind of match with the northern part of Breda Martis. You have this clear asymmetry where one side of the rift axis is sitting a lot deeper than the other. You have that rift axis in the first place. It's a similar degree of width. And also if you look at it in map view, it might be kind of difficult to see for everyone in the back of the room, but there are what appear to be some sort of fracture zones that link up these rift segments. But this is kind of a unique feature on the surface of Venus that does not represent almost any of the other rift systems across the planet. Now, the over-thickening regime. And this is why I brought up the Coronae earlier. If you end up in a situation where you are adding more material than you can create the accommodation space to make, so yeah, if you're adding more material than you're creating new accommodation space, what ends up happening is that you over-thicken the crust. The root of that crust transitions into eclogite phases. And because eclogite is a lot denser and it's a lot weaker, it collapses down into the mantle, and you get this topographic inversion that looks like this, right? So you start off with this peak, you get these flexural troughs on the side, and then when the collapse begins, that peak inverts. But you maintain those troughs because what was before being created through flexure is now being created through sustained, like, dynamic topography, because you have these lithospheric drips that are downwelling. And then you have this elevated bowl-shaped interior that is a little bit elevated above the background, that is then divided by these, troughs and elevated rims. And that's really interesting because there's a lot of features on Venus that look like that. The Coronae look like that. So there's a bunch of different varieties of Coronae. Like I said, it's a morphological term. There's a lot of different varieties with very different topographies. But when you look at, these are all the different, over-thickening cases that we ran in the model, some of these start to look really similar to the Coronae that have been identified in the literature. And that kind of implies that if this is true, then like delamination due to eclogitization might be really important and something that we need to consider when we start thinking about the origins of these features, which are unique to Venus and therefore may tell us something about the overall tectonics. So here's Anahensic Coronae on top, Atete Corona on the bottom. You can see, like the two profiles at the top are across Anahensic and Atete. At the bottom is the model that I had on the previous page, that over-thickening model. They do have a lot of the same diagnostic features, that bowl-shaped interior, that trough on the outside, these elevated rims relative to the trough. It is a decent enough match if qualitative. You go to some other Coronae like Miralegi and Taranga, and you have a similar kind of feature where you have these troughs, these outer rims, this bowl-shaped interior, like from the previous model on the other page. But this model is a bit different. This model, it's not as elevated, and there's a lot more complexity here. There's a central peak. That central peak might show up in some of the other Coronae, like Miralegi up here. And there's a lot of different models that don't have this elevation. And so while morphologically they can be similar, like the actual elevation is fairly different from any of these models. And I think the reason for that, if you cast your mind back to was explaining how the model works, we're not modeling melt generation. We're just prescribing a rate of a new addition in the model. So as a result, there's no dynamic uplift. There's no melt there's no upwelling that is going to push topography up if this is an active feature. So this, if you bear with the hand-drawn model for a second, so this was kind of the model that we came up with for some of the Coronae, the rift-associated Coronae. This idea that maybe you have a plume coming up, or maybe there's just some other form of upwelling, creates new melt. This melt comes up through this through the lithosphere, adds new material, thickens it. There's not a whole lot of extension because there's no subduction on either end to actually pull the plates apart. And as a result, you just kind of over-thicken things until you start forming this eclogite root, and this eclogite root wants to drop off. And then that might be how you create some features of some coronae on Venus. So this cartoon is derived from the model. So what's interesting though is that this might be a form of recycling, you know, where like before I mentioned how there was no, you know, before I mentioned how like, okay, so on Earth, you're creating new material all along, you know, the mid-ocean ridge, and it's being laterally migrated and then subducted and therefore destroyed, you know, down at the subduction zones. If you're not creating new crust at these rift systems, except in these specific locations where coronae are forming, maybe because there's a plume underneath, right? Then what that means is that they're also getting recycled right where that new material is being formed. So just how I had like the subduction zones outlined in white, areas where stuff might be getting recycled on Venus is outlined in white here and seems to be, or could be, where you're actually adding new material. So it's all co-located and very regionalized. So yeah, so this is all just kind of, you know, what I had previously said. So to summarize, it's not a good analog to the mid-ocean ridge. Model does seem to work for some of the coronae features, but that maybe says something about how regionalized crustal recycling is on Venus and how it's very much not like a mid-ocean ridge. So here's part 3, the second half of the Venus stuff, which is in progress. And I'm really excited to kind of show this with the limited amount of time that I have left. I already emphasized that coronae are not a single thing, right? There's a lot of different variety. I'm really focused on this kind, the stuff that's embedded in the rift. They're asymmetric, they're polygonal, they have these raised interiors with these elevated rims and these really sharp boundary troughs on either side. So here's an example of that is Taranga. Here's the geological map that shows the lineae. If you take the lineae as as telling you something about the stress field, they seem to form along with the rift. And it's also very distinct from the surrounding coronae. So this is the kind of corona that I'm really interested in. There's a whole bunch of these all over the surface, from Artemis to Quetzalcoatl, Atete, Taranga. There's a whole bunch. And they all seem to be embedded within this global rift network. And they all have this fairly like generalized, but like, you know, they all fall into the same category of corona where they're either these like large plateaus or these kind of these subdued plateaus without that much of a trough. The idea is that these might actually be a time series of some sort where you start off with an active corona with high topography, you get this big plateau type, you know, with a positive gravity anomaly from free air because of the higher topography. And then when like the plume shuts off or whatever the source of melt shuts off, this thing isostatically relaxes. The topography lowers, the boundary troughs, which are being sustained by this downwelling, disappear. And the gravity anomaly kind of for free air goes to 0, and the bouquet should go to 0 as well as you get rid of the dynamic, you know, downwelling. So this is the idea. So we're running a whole new set of models that actually do model melt generation now. And we take the area of the melt, convert that into a, you know, absolute value of the melt, create a dike up through the surface. 20% of that is flows on the top. 80% of that is new material to be added to the crust. It was black in the previous ones. It's purplish blue here, but that is eclogitization. And you actually start to get a similar feature that we showed before, where these two sources of downwelling occur on either end of the plume. And topographically, you end up with something that looks like this, where you have this, you know, 1.5 to 2 kilometer high, you know, profile, and then as the whole system shuts off, it collapses down. So you get this more subdued profile without very much trough on either side, which is very similar to the cartoon that I showed before. So right now I'm in the process of going through, and this last like 3 minutes, of going through all these different rift embedded coronae on the surface, keeping track of what is their average elevation relative to the surrounding plains, what's the free air anomaly like, what's the bouquet anomaly like, and seeing whether that matches up with the predictions made by the models. Preliminarily, what you end up with is circled in yellowish white is these areas of fairly high topography, fairly deep troughs embedded within the rifts. And then in red are coronae that are embedded in the rifts that have fairly low topography. The trough is pretty, subdued to non-existent. And so, and they cluster geographically. Whether or not this is a real signal is remains to be seen, because when you look at free air anomaly, what you end up with, and it's kind of hard to tell in this image, but what you have is these areas of high positive anomaly in the supposedly active coronae, and then it's fairly subdued in the red circles where like we hypothesize that there's not very many active coronae, that rift system might be somewhat dead. So one of the things that I really want to do is I want to go through this more systematically. I didn't have time to get it done before this talk, but I'm really excited to show that when the time comes. But they do seem to kind of like these two types, I can now put numbers to them. Of this, that active type, you're generally more than 1.5 kilometers elevation above the surrounding plain. You get this big plateau type. You get a positive free air anomaly of about greater than 50 milligals. For the inactive, quote unquote, type, it's less than 1 kilometer, sometimes down to 0.5 kilometer. You get that subdued topography. You also have a positive anomaly that's less than 20 milligals. And then next step is to start looking at this stuff in Bouguer and start interpreting that. But that's difficult because this is the resolution of gravity anomaly for Venus. It's highly variable across the surface. And you have pretty good up to like maybe 90 something degrees in the interior, around the equator, but in the southern hemisphere and the northern hemisphere, but especially in the southern hemisphere, it can get all the way down to like 50. And what that means is that features that are less than like 300 kilometers become almost impossible, if not completely impossible, to resolve correctly. So interpreting the Bouguer and free air anomalies to kind of to match up with the models becomes very, very difficult. But one of the things that could come out of this is we could start making predictions for future missions. So the Veritas mission is going to improve on that global map within the next decade. And it's going to be amazing. It's going to fill in those holes. We're going to get higher degrees. We might actually be able to resolve these features in free air and Bouguer. We also, because it has INSAR, will be able to get deformation of the surface. There's a similar story with the VENSAR instrument on board Envision from the European Space Agency, which also comes along with a ground penetrating radar. So we'll be able to make predictions from these models that can be addressed by future missions and future data sets. And yeah, that is, and then to tie it all back together is my last slide. To tie it all back together, what I think the big takeaway of all this work is that these relatively small changes in heat flow, surface temperature, thickness of the crust can end up manifesting in completely different styles of global tectonics and geodynamics. And I think that's really interesting, and that's kind of what's motivating me to keep on working. Thank you very much. That is the end of the talk. I'm happy to take questions. Thanks.
I don't know who that was.
Someone said something online. Yeah. Oh, hi, Sean. Okay, yeah. If anyone has a question. Yeah.
So on the surface temperature, and Rachel, by the way, but on the surface temperature, how did you treat that? Did you deal with lapse rate, or did you deal with line varying surface temperature?
We set the surface temperature in the models to 470 and didn't vary it across the surface, because Venus's atmosphere is pretty thick. There's not a whole lot of variation across the surface. So we essentially like anchored the geotherm to 470 at the top, and then we have like a free boundary at the bottom. So it's allowed to vary depending on kind of what happens in the model.
But there is a bit of a variation with lapse rate, right?
What do you mean by lapse rate?
It just gets cold as you get higher in altitude.
Oh, yeah, sure, but we're not modeling the atmosphere, like, at all.
Okay.
We're just looking at, like, this, the top of the model is the top of the geosphere.
Okay,
Yeah, we're not modeling atmosphere at all.
okay.
Though we do apply a pressure, but it's like a uniform pressure across the surface. Yeah, sure.
So the Magellan topography, especially in the rift areas, sucks.
Yes,
How-
a
how
lot.
did you deal with the uncertainties with it?
We tried the best we could, which is basically we picked segments along the rift that seemed structurally pretty similar. And then averaged across that, basically averaged the along strike variation to hopefully come up with a topographic profile that was close to average. There's really not that much we can do about how much it sucks in other respects, especially around the rifts, right? With only left looking radar, there's only like so much you can do. My understanding is that new data products are going to be coming out because people are taking a second look at Magellan ahead of the new missions. So I'm looking forward to when that data set comes out. I would love to play with it, but right now I can only do so much, and I have whatever I can, and I haven't done that much more than what I've already said.
I like an ensemble statistic question.
Yeah.
So I think it was in your second chapter, you said that there's like this diagram, you have like 3 different regimes.
Mhm.
And it's just like a handful of case studies. However, a lot of the plots that you showed, seemed like it was like 500 plus like members. Like what made those?
What do you mean?
Like 500 different like model runs? Or how many?
Oh,
different
no.
model runs?
There was only 18 model runs.
Okay.
If you're thinking about the like hundreds of points, that's the actual topography.
Got it. From like one or like different?
Wait.
Sorry, I was just kind of.
Are you talking about?
Yeah.
Are you talking about that? That's time.
Can you go to the like 2 slides forward? There.
Yeah, these are just cross sections of the actual topography
Mhm.
that have been stacked.
Okay.
That's all that is.
From one model.
Not from a model run, from the actual
From the
Magellan
actual- okay, I
topography.
see, I see.
This is the model in blue.
Mhm.
This is all real.
I'm gonna ask a stupid question.
Yeah.
How do you know these linear sinuous features are in extension rather than compression? Could these be compressional ridges or?
They're probably not compressional. You can see displacement of craters and of volcanoes across them where they're clearly extensional. And also, if you look at them in the limited amount of profiles that we have, it is very clearly like they're either half graben or full graben where the bottom has dropped out. There's these like really strong scarps. Yeah, there are compressional features also on the planet. They look very different. Yeah.
Since you're here, I think, is it the next slide or around here, there's one where you're, yeah, that's it. Yeah. So, you're talking about this bowl feature. I think I asked this before, but I forget the answer. In the bottom there, the feature that's not captured, that's predicted in the model, which doesn't show up at all, this like W.
Oh, yeah.
Can you
This
talk
thing.
about that?
Yeah, so in the model, right, we have no dynamic uplift. We also have, in this version of the model, we also have no like sedimentation or lava to infill anything. So this is probably like an artifact from the fact that like we're not making any new material that can flow. Otherwise, this would all be infilled or maybe wouldn't even form because you should be having like uplift that creates something very different. So like if we fast forward to the slightly more realistic model that I am still working on, this one that actually has the melt flows, and you look at the topography, that W ceases to exist. So I think it's an artifact of the way that we formulated spreading in the first model.
That's a good one.
Yeah.
And then does that also smooth out the troughs on the outside, or does it melt it out there?
Yeah, it smooths the troughs on the outside as well, for sure, which is something that I'm kind of interested in because the troughs disappear a lot. So now I'm wondering like, oh, are the troughs that we actually see in the actual topography, is that, are those like other rifts that kind of, circle around the outside of these features? Are
They're
they
more subdued than the one in the model.
these ones? Yeah, are more subdued.
I mean, like, if you go back to the other slides we're looking at.
Yeah.
Also
This stuff.
have the- Right, the
Mhm.
trough on the left there, for example, it's not as deep in the data as the models.
Yeah.
That's
Mhm.
the story.
I mean, it could be. There's a lot of variation. I'm still trying to grapple with a way to like, okay, how do I do this in a bit more of a quantitative way? Because at this point, I'm just kind of looking for these, what I believe are diagnostic features across these different, topographic profiles and across these models. But to do that statistically is a little bit more challenging. And there's a lot, because there's like 18 models and I have something like 36 different like profiles, and comparing all of these, the number blows up very fast. So I'm still working on doing that in a way that makes sense.
Anyone online?
I saw like a chat. Where did it go? Oh, thanks, Cole.
Hey, Nick, I'll ask one quick one. At least I think it's quick. How are you guiding the volumes, I guess, of the eclidization of the downs in this? What's the parameter that you're tweaking?
Yeah, okay, so what we've essentially done is we've created a piecewise function that maps out what the eclogite phase space should be on Venus. And any basalt basically any basalt that crosses over that line is recoded as eclogite with a whole bunch of different rheological parameters, and then behaves as it's, supposed to behave.
And I guess the follow-up then, is there inherently a strength or a connection between the part that's gone to eclogite relative to the basaltic part that has not yet? In other words, does it have a slab pull kind of dynamic as it starts to go down?
Yeah, let's see, I'm gonna go back to this one and kind of show, yeah, there is a bit of that. Where what happens is I think like this eclogite drip falls and then drags some of the basalt with it, and then drags it into that regime where it should be able to eclogitize. And it kind of runs. So there's Harm, you once called it like, oh, Harm's not here anymore. Harm called it like phantom subduction once, because it's not really slab pull, but it's kind of acting like a really small version of a slab, but it's not coherent.
Yeah. It's more from a flow perspective than a coherent plate concept, I guess. Yeah. Neat. Okay. Thanks.
This model needs to be improved as well, but this is kind of the preliminary stuff.